Okay, so if you recall when we started chapter 6, we were talking about how that we were kind of starting a new unit where we're trying to understand properties of the electron in chapter 6. Chapter 7 gets into properties of the nucleus. When you look at electron configuration, you may not think much changes. If you think carbon's a 1s2, 2s2, 2p2, nitrogen's a 1s2, 2s2, 2p3, doesn't seem that much different. 2p4 doesn't seem that much different. What's the difference between 2p5? But if you go from like lithium to beryllium all the way across to neon, you realize that you really do change quite a bit for your atoms. You go from being metals to metalloids to non-metals to then being completely happy as gaseous atoms at room temperature. You have non-metals like carbon that can be solids up to 2000 plus degrees C. Then you have non-metals like O2 and N2 that have boiling points well below room temperature. So, we have a wide set of properties that vary as you go from left to right across the periodic table. Chapter 7 is going to help us understand what some of those differences are in the nucleus that help play a role in drastically changing those properties from left to right. So, from electron configuration standpoint, we may not realize that there's a lot of difference between a 2s1, 2s2, 2s2, 2p1, 2s2, 2p2. Those may look very similar to each other, but we'll see in terms of trends of our nuclei that the atoms end up having a very different property as a virtue of their position on the periodic table. And then once we get through chapter 7, we'll then get into actually trying to analyze the structures of compounds, how strong are ionic bonds, how does it relate to the size of the ions, and then probably more to the point, like what do our molecular compounds look like in terms of their bonding? So can we start to characterize Lewis structures, learn how to write Lewis structures, and then get into chapter 9 where we can start to three-dimensionally try to picture some of those structures. So that's kind of the lay of our layout. We're trying to get through chapter 9 for midterm 4, so the next midterm. To also then think of the schedule for a moment. The day before midterm 4, so the Monday before, that day is Veterans Day, so we don't have class that day. We'll probably think when we get closer to it on how we might do a review. We can either do one on Zoom on Monday. I don't think you guys want to come in Friday at 7 a.m. So probably we'll do something Monday via Zoom. They won't unlock doors on holidays here, so we really can't get into a classroom that day. Just to have that kind of on our radar. And in chapter 7, we're only going to cover the first 4 sections of chapter 7. We're going to cover them also pretty quickly as well. And so we're just going to try to talk about a quick little overview of the periodic table, a little bit of a timeline on when things were being determined with the discovery of a few different groups of elements, just to really set the stage for kind of like when we were learning about our elements in the periodic table. We'll talk about something called effective nuclear charge. This will be the primary trend that gives us our periodicity. This will be the primary trend that shows as we go from left to right, we go to metal to non-metal, then we start a new row, we start over again. And so this will be the main kind of periodic trend that shows us periodicity. This is where the periodic behavior comes from. Cannot write today or any day. Periodic behavior is what I'm trying to write. Comes from the effective nuclear charge. Then we'll get into how atoms vary in size. We'll compare their size of their ions. So we'll be comparing things like Na size versus chlorine, but we'll also be comparing those versus their cation sizes versus the anion. So we're going to try to see how this probably makes sense. Like, can you think of the size of sodium versus sodium plus? If we take an electron away, makes sense it becomes smaller. So taking electrons away, going to cations makes atoms smaller. And then you can probably imagine if we took chlorine, whatever its size is, we throw an electron into it, it's going to make it bigger. So going to negative ions tends to make things bigger. So when we see sodium to sodium plus, this is usually becoming smaller. Chlorine to chlorine minus, this is becoming bigger. So just to kind of set the stage for how we can even just think about some of the size of atoms from a few things we already know. And then we'll get into ionization energies and electron affinities to wrap the chapter up. How much energy does it take to remove an electron? And so that's ionization energy. So this is losing electrons. And then gaining electrons is electron affinity. So the energy associated with absorbing an electron is electron affinity. So just a quick overview, we'll define these more precisely as we continue. And so let's kind of introduce a few different thoughts on the periodic table. If you look at the discovery, like the first discovered elements were in ancient times. I think we were talking about how the old way of trying to discover an element was burning things and trying to see what you can reduce them down to. When you finally got to something that you couldn't break down further, you knew that must be an element. And so the ancient time elements are things like iron, copper, zinc. You don't need to memorize these, but it's just kind of like showing you some of the elements that were first discovered were the things that are a little bit more prevalent in compounds, especially in, if you think of things that are in minerals, there's gonna be easier for scientists to burn and get down to a single substance. And so those are the or not metals, some of them are non-metals, but those are the substances first being discovered. And then if you get to right around the discovery of the periodic tables within, the periodic table itself is being discovered in about 1870. And I like to set the stage for that because that's a good 30 years before the discovery of the electron. And that's a good like 10 years before, later after that for the discovery of like atomic number and the whole idea and concept of what protons were and how that's what really varied between atoms being their protons. So the periodic table is being laid out well before there's any kind of knowledge of electrons, electron configurations, even the concept of mass number wasn't known at this time. But what was known was you could calculate a mass per particles. They were able to work that out. You can get reacting units. That's how they were getting kind of like the number of moles and getting like almost like a molar mass. So they're able to arrange a periodic table by increasing molar mass, but then grouping then in terms of vertical columns of things that were similar in their properties. And so they were beginning to align the periodic table just by groups of elements that were similar in properties. And they were leaving gaps whenever they kind of wouldn't have an element to fill in with its sort of properties vertically from top to bottom. So they were seeing a lot of similarities, but not always, but a lot of similarities between like the halogens, the copper, silver, gold kind of being like almost like a stable group for our transition metals was being, kind of used to kind of position them on the periodic table as well. And so if you then notice, we have a good number of elements within the time period of when we're discovering the periodic table to then afterwards that weren't even known. So we only probably knew about half the periodic table at the time of the actual that the periodic table is being proposed as an idea. Mendeleev being the one, the scientist credited with the sort of arranging the elements. And Moseley then later was bombarding elements with electrons, finding an X-ray signature. This is ultimately how we determined mass number. So probably not a Jeopardy question because it's a little bit too intricate, but Moseley would be credited with discovering the mass number or the atomic number maybe is a better. So the atomic number coming from Moseley, seeing this like signature emerge that was proportional to the number of protons within the nucleus. And so this occurring within the late 1800s to the early 1900s. Okay, so I think the takeaway here is that the periodic table is being proposed well before most of the elements are discovered, and then was predicting the discovery of other elements, and then was well before the discovery of the subatomic particles. And so then why do the trends vary from left to right and then reset from left to right with each row in the periodic table? We've already seen that the alkali metals have a very similar trend in how they react with water, and that those metals do react differently than their neighbors, even the alkaline, react with water in a much different way. If you remember, the alkali metals were very reactive with water, so much that the potassium kind of lit on fire, but the alkaline metals just reacted very slowly. So why do we get this difference, or why do we get this similarity of properties for atoms in the same group? Well, let's take a look at effective nuclear charge. So nuclear charge is Z, so effective nuclear charge we call Z effective. So the Z effective or effective nuclear charge is sort of the charge you imagine the valence electrons get to experience. So our nuclear charge for sodium, so the plus charge here is 11 plus, and that's coming from the 11 protons in the nucleus of the atom. So we have a nucleus that has 11 protons within it. And then you can think the 1s2, 2s2, 2p6 electrons. So when I'm looking at these electrons here that are in the 1s, the 2s, and then the 2p set of orbitals. So we have the 2p set of orbitals here, that those negative electrons are absorbing a lot of the positive charge and kind of preventing the outer 3s electron from experiencing that full positive charge. Now, the one thing that you might recall from the 3s electron, let me choose a different color here, let me choose red. And so remember these radial probability functions. So this is maybe the one place where you can make some understanding of radial probability distribution functions, is that even though the 3s electron is very big compared to the 1s2, the 2s2, the 2p set orbitals, there's still a little bit of probability that it's relatively close to the nucleus. And so these electrons here are experiencing some bit of that 11 plus charge. And so how much of that charge makes it out to the outer valence electrons is about the nuclear charge minus the number of core electrons, but that's going to be an over approximation due to primarily those two little like blips in our radial distribution function where those s electrons have some probability of being relatively close to the nucleus. So when we look at the effective charge, you can approximate it. This is not the best approximation, but it kind of lets you see the trend from left to right very easily. If you take Z effective to be the nuclear charge minus the core electrons, when you go from left to right, you see the core, especially for the first two rows. When you're looking at the first row for like lithium being a 1s2, 2s1 to say all the way to fluorine, 1s2, 2s2, 2p5, let's make sure to define what a core versus valence electron is. So a core electron is anything that's not a valence electron. So if we're counting valence electrons for lithium, we'd have just one for here, and then our outermost shell electrons for fluorine. So this is a fluorine atom, that would be 7 valence electrons. And then if you take the core electrons for these atoms, it's just 2 electrons for each of them. So they each have the same core. And so then when you think of lithium's Z effective versus, so lithium versus fluorine, lithium Z effective would be, its Z is 3 protons in the nucleus, core is 2, so the outer electrons experience a charge of about +1 units of charge. And then if you think of fluorine, fluorine has an atomic number of 9, still only has 2 core electrons, so it has a +7. So the difference between lithium and fluorine is fluorine's outer valence electrons experience a much higher effective charge. And so even though fluorine has more valence electrons, think of how those electrons have to experience a greater charge. And so if you're comparing lithium versus fluorine, what you can say is that the fluorine, in terms of size, we're going to jump ahead and think about size real quick here. We don't talk about size for a few slides from now in terms of a main periodic trend, but you can see that lithium is going to be bigger than fluorine because it doesn't have as high of a charge to pull those electrons in. Fluorine has a very big charge, and it pulls those electrons in tightly as a result. And then that's also why fluorine really wants electrons. We're going to see this soon, that fluorine, it's more in chapter 8 that we'll see it, that fluorine has a very strong desire, the most out of any element on the periodic table that forms bonds, to try to pull electrons towards itself. This is why fluorine's almost anything with fluorine in it is going to be hazardous to work with in the lab, because fluorine is such an atom with a strong pull of electrons towards itself. This is one of the reasons why HF's nasty to work with, F2's nasty to work with. But anyways, in terms of size, lithium's bigger than fluorine as a result of it having a lower charge. So the effective charge is it pulls those electrons in more tightly for fluorine. If you then think of the energy it takes to remove electrons, it's going to be harder to pull an electron off fluorine than it is lithium. Lithium's going to give its electron up more easily, not without energy being required. It's still going to take energy to remove it, but less energy than fluorine. So we're going to see that our left side elements give up their electron most easily, but not without any energy cost. And then the right side element's going to take a tremendous amount of energy to remove their electrons. You're going to see probably the corollary. The nonmetals can absorb an electron most favorably, so they're going to want to absorb electrons to go to anions, and our left side elements are going to want to lose electrons to go to cations. Okay, so let's get back to talking about the effective charge itself. This slide here is kind of trying to show you the idea we were just talking about with our 2s orbital has, if you think of the chapter 6 question, could be how many radial nodes? We didn't talk about that earlier, but if I'm looking at these plots here, my 1s is here, so there's no radial nodes for the 1s, so the radial nodes, we would probably only ever ask this for s orbitals, but the radial nodes for the 1s is 0. For the 2s, you see the 1 node here. And if we continued for the 3s, there'd be 2. And the 4s, there'd be 3. So if you're asked about radial nodes, it's just the n value minus 1 for s orbitals. If you then look at the p orbital, there's no nodes here. So if you go to 2p, there'd be 0, 3p, there'd be 1. I don't think they'd ask you about this, but the 2p is the one that has 0. If you were to go to the 3d, it would have 0, 4d would have 1, etc. So the first time you have a subshell, within that n value, it's equal to 0 in terms of the radial nodes. A different question we probably wouldn't ask it is planar nodes. That's from the L value. So the L value tells you the planar nodes. So S would be 0, P would be 1. That's why there's one set of lobes for P. 2 for D, that's why there's 2 sets of lobes. 3 for F, that's why there's 3 sets of lobes. But the whole point here is to try to show you that the S orbital having this probability here, I don't know why I'm using the same color. Let me switch colors here, just to see that for the 2S, we still have some relatively high probability that one of those electrons is relatively close to the nucleus. So that's why this is an approximation. If it weren't for that, this would probably be a pretty direct equality. We'll see on the next slide, there's some more advanced methods for calculating effective charge. But the idea is that effective charge is going to increase from left to right until we get to the noble gas group, then it's going to reset itself. When we get to the noble gas group, you're going to see that their noble gas is relatively small from left to right. Like neon's generally smaller than a fluorine atom, but it doesn't have any room for electrons to take more electrons. It doesn't have an easy ability to lose electrons. So it's very happy just being the monoatomic gas. And then we reset the properties. When we go to the next row, 1 valence electron, big core, bigger size. So we reset our size. So we go small, across from left to right. Then we go to the next group, and we go back to a big atom, and then repeat the process. And so if we look at some advanced methods for calculating our effective charge, so this first trend here is showing you that as you go from lithium on across to argon, if you're thinking you're just going from 3 to 4 to 5 upward protons in the nucleus, you get all the way to argon. This is 18 protons in the nucleus. And so one of the things you can do is you can say, well, what's the charge that's experienced by the 1s shell electron? So the 1s electrons are the ones that are closest to the nucleus on average for a given element. What charge do those elements experience? And it's nearly the full nuclear charge. And so for lithium, it's about +3. And for argon, it's not quite +18, but you can think the reason why it's not exactly +18 is a little bit of charge that those elements with their radial distributions that are close to the nucleus are absorbing a little bit of charge. So we're not getting a full charge, but pretty close to it for the 1s shell. And then for here, these are looking at what's the Z effective for the valence electrons. So you can calculate the Z effective for any electron in an atom. So when you say what's the effective charge, usually you either say, if I just say what's the effective charge of sodium, you're probably by default you're thinking for the outer 3s electron. And so let's think about sodium for a minute just to kind of start here. And so for sodium, we'd have a full configuration, 1s2, 2s2, 2p6, 3s1. So when we say the Z effective of sodium, we mean for the 3s electron, because that's its outermost electron. And so, but then I could say, well, what's the Z effective for the 1s versus the 2s versus the 2p versus the 3s? And so the first thing you can say for sodium is that the Z effective would go like this. The 1s experiences the greatest charge, then the 2s a little less, the 2p a little less, and then the 3s experiences the least charge. So in other words, the outer valence electrons, or the biggest electrons on the atom, experience the overall lowest effective charge. The elements that are closer to the nucleus experience a greater charge. This might get a little bit off topic, but if we jump up to something like titanium real quick and just kind of go through the 1s2, 2s2, 2p6, 3s2, 3p6. Remember then we go 4s2, 3d2, because titanium is 2 across into the transition metal group. And so the reason why I wanted to think about titanium real quick is, well, what do you think here? Which one of those do you think experiences the greater versus lower effective charge? Or of titanium, which of its electrons do you think experiences the overall least positive charge from the nucleus? Probably the largest orbital, which is this one here. So the 4s is the larger orbital. How do I know that? Well, the 3D is the n equals 3 shell. That's smaller than the n equals 4 shell. And so when you're thinking of titanium in terms of its size, you're thinking, 1s2, 2s2, 2p set of orbitals, 3s, 3p set of orbitals, and then 4s is out here, and then 3d would be in this space here. So 3d is closer to the nucleus. Closer to the nucleus absorbs would have a greater effective charge. It's experiencing more effective charge because it's closer to that nucleus. 4s on average further away, therefore experiences a lower charge. So if we're doing this ordering for titanium, we'd have 4s would experience the lowest charge, then the 3d, then the 3p, then the 3s. And this is the D are going to be a little further away on average than the P, a little further on average than the S. And then just continuing along 2P, 2S. And then the, I switched my directionality of my signs. So let me continue that as we go to a smaller subshell, that those electrons are experiencing a greater effective charge, such that the 1s experiences almost the full nuclear charge, the 2s a little less for the 2p, and then by the time we get out to the outer valence electron, there's not much positive charge holding those electrons into place. Okay, now, one way to calculate the effective charge would be the Z minus, so the nuclear charge minus all of these electrons counted up. And so for titanium, you could say, well, this effective charge, maybe it's going to be about the plus 22 nuclear charge minus the 20 electrons in this range here for about plus 2. So you could approximate it that way, and the approximation lets you see that you can kind of, from left to right, get a trend that our effective charge from left to right is increasing as we go across the periodic table. Okay, now let's just come back to, again, back to sodium. So sodium from neon is the one that had a really high effective charge because it ended our row. Whereas we go from left to right, neon was really high. We reset sodium down back to low. And so when we compare a few different ways of calculating sodium's effective nuclear charge, one of them is with the Z minus number of core electrons. That's the green curve. So the green curve is the approximation of just taking the Z 11 minus 10 core electrons. If you go to magnesium, it would be 12 minus 10, 13 minus 10 for aluminum. If we continue to silicon, 14 minus 10. So as we go from the green, we're just linearly increasing in our effective charge. And then there's two other more advanced ways. There's something called Slater rules in the books, which I'm not going to go over. That's a way we could try to calculate more precise values for effective charge. And then the blue curve is showing like a computational method for doing this that we don't show you. We talk about that there's just a computational or more advanced theoretical way of calculating the effective charge. But if you notice, the blue and the yellow curves are just increasing just with a little bit of pattern to it. So when we look at our curve for the green, you see an increase in effective charge from left to right. And then with the blue and the yellow, you're seeing an increase as well, just it's a little bit more nuanced. And so you see those increases from left to right. So when you look at the blue and you see that the effective charge for sodium isn't quite +1, but it's maybe like +2 or +3 units. That's because the 3s has a relative probability of being closer to the nucleus, that it's absorbing a little bit of positive charge from that radial distribution function. And then if you compare this to this, if you compare lithium to sodium, you can see as you go from the 2s to the 3s to the 4s, you are getting a higher and higher probability on average of being a little bit closer to the nucleus and absorbing some charge. Okay, so what can we say? So some of the conclusions I hope that we can walk away with are that our core electrons screen the nuclear charge from the valence electrons. So it's the core electrons that the idea is they're screening charge. They're like getting away. They're absorbing or dampening some of the nuclear charge away from the outer valence electrons. The outer valence electrons do not screen each other that effectively. That's why from left to right, it's just Z minus the core as being a good approximation. And then our Z effective is increasing from left to right, and that resets with each row. And it's that resetting of the effective charge that resets our nuclear trends. It's like the difference between having a low versus a high effective charge has a big difference on properties of our atoms. And then the core electrons in larger orbitals are poorer screeners. So when we get to like a 2s, a 3s, a 4s, they have some probability of being relatively close to the nucleus. They're kind of absorbing a little bit of the positive charge. And so we get a slight increase from top to bottom. This is almost inconsequential. This doesn't have too many impacts, but as you go from top to bottom, you do get a small increase in the effective charge. There's a couple of ways this will play out later, and I'll point out that there's a few instances in the periodic table where you can see a couple of trends that you may not have predicted if you didn't know this detail here. But you get a small increase from top to bottom in the true effective charge. If you calculate or approximate Z effective minus the core, then it would be +1 for lithium, +1 for sodium, +1 for potassium. But you see that you get a small increase as you go from top to bottom in the true effective charge. Okay, so then how does the atom size kind of like how's that related to position on the periodic table? Well, let's first talk about how atom size is sort of impacted by the fact that most of the elements in the periodic table form bonds. And so the non-bonding radius is the radius that an atom would have in a non-reactive collision, but there's not too many atoms that non-reactively collide. That would be like two heliums colliding. So you take two heliums, and it's kind of like how close can these atoms get when they deflect off of each other? That's what's defined by the non-bonding atomic radius. And so when you think of the non-bonding radius versus a bonding radius, when you form a bond, atoms overlap and the nuclei get closer together than they would in a non-reactive collision. So if you look at a bond here, if we draw a circle around, so the circle would be kind of the size of the atom when it's not bonded with anything. When it forms a bond, say with itself, the bond length is shorter than 2 times the non-bonding radius. So in other words, when we make bonds, the atoms get closer together due to the way we'll maybe see some different bonding models, but their orbitals start to overlap with each other is one model. So we can imagine that the nuclei are pulled together in that process. So the bonding atomic radius is, if you had the same atom, if you had like Cl2, let's say you have 2 chlorine atoms bonded together, you take the bond length, divide by 2, that's the bonding atomic radius of chlorine. Then the non-bonding radius, so if the atom didn't form a bond with itself, that would be larger than the bonding radius. So if you think of the radius non-bonding, that would be greater than the radius of the bond. And the only reason I'm bringing this up is when you look at a table of sizes of atoms, you can either look up a table of the atom size where they're not bonded with anything, or you could look up the atom sizes where they're bonded with other things. And then you have to have like a bond type because some bonds are single bonds, some are double, some are triple, and the nature of bonding will change the bond length. So this gets a little bit ahead, but you might be able to make sense here today, and we'll see this later. If you had like a carbon-carbon single bond versus a carbon-carbon double bond versus a carbon-carbon triple bond, that this bond here would be the shortest bond, this would be the longest bond. So the type of bond matters, but the problem that we have is that we don't know how to sketch Lewis structures yet. So if I just show you a structure, you may have a hard time interpreting single versus double versus triple bonds. You may not know what that means, so we'll circle back to bond types later and kind of talk about trends. But you can sort of maybe understand that there could be double versus single bonds that would play a role in bond length. So when I show you a table like this one here, that this table here is assuming that we have atoms that are single bonding with each other. And so this is looking at the bonding atomic radius for single type bonds for all these elements and comparing their sizes. Now the reason why I went into this to talk about bonds is because this is a nuanced table, right? When this is a bond type radius, and we're trying to use it to kind of say that these are mostly related to the size the atoms would have if they were their non-bonding radius. So the non-bonding radii of these elements would probably follow the same trends. If I could plot the non-bonding radius for all these atoms, you would probably see the general decrease in size from left to right. But you can see that lithium to beryllium gets smaller, and as we go to boron, we get even smaller. So we get from left to right a decrease in size. And the only one thing that might seem a little bit strange is then you get a jump in size for the noble gases, but that's just an artifact that they don't form bonds. The other radii were the shorter bonding type radius. So if we were to plot all like non-bonding radius, and we would see the halogens be bigger than the noble gases. So I just want you to see that it looks like the noble gases are kind of breaking the trend, but they really don't. It's a nuanced trend that we're looking at bonding type radii, and then our noble gases don't form bonds. So they don't have a bonding radii because they don't form bonds. And so we get a decrease in size from left to right. I would say it continues through the noble gases, but the non-bonding radius would continue through the noble gases, but they don't form bonding radii. But you see that their sizes are kind of right in the order you would expect anyways. And so a decrease in size from left to right, and this is because the Z effective is increasing. So if you go from lithium to beryllium, higher charge, smaller size. Boron, higher charge, even smaller, and continuing all across to neon, to fluorine and neon being really, really small with really high effective charges. And so then if you think from top to bottom, of course we're going to increase in size because we're just adding on layers of electrons. As you go from having a 1s to having a 2s, having a 3s outer orbital, we're increasing in size as we go down a group. So if you notice, we go down, there's no break in our trend. We increase in size every single time. So we're increasing in size from top to bottom. That's just because we're packing more and more electrons into an atom. Electrons repel, so that's pretty straightforward that we would increase in size from top to bottom down a group on the periodic table. And so we're just having more and more core electrons. Electrons repel, so we're going to certainly increase in size. But now, I like to then circle back to, as you go from lithium to fluorine, you're also increasing in electrons, but you don't increase in size because it's not necessarily just about those electrons' repulsions with each other, but how they're fighting towards that positive charge that's higher, and that pulls them in to be smaller. So our size decreasing left to right, increasing top to bottom. And then this is now getting at the size of cations versus anions that we were alluding to on our opening slide, that if you take an electron away from an atom, so if you go from lithium to lithium plus, as shown here, of course you decrease in size. You're going from lithium being a 1s2, 2s1 to just being the 1s2. So you're going from, a configuration that's a 1s2, 2s, and then you're losing the 2s, so of course we're going to decrease in size as we lose an electron. Even if you go to just losing one, well, I guess beryllium-2 loses both the 2 electrons. So beryllium to beryllium-2 plus goes from a 2s2 down just to the 1s2 outer configuration. So it's like you're going from helium plus a 1s2, helium plus a 2s2 to losing the 2s2. Of course, you're going to be smaller. And then continuing to bismuth 3 plus. Now, if you do the opposite, if you add electrons, you're adding to the particles that are fighting for that positive charge. You're adding to the negative particles that repel each other. So I don't think it's too crazy to think that every time you add an electron, you're going to add to the size of an atom. So oxygen to oxygen 2 minus, fluorine to fluorine minus, we're growing in size. So cations are always going to be smaller than their parent atoms. So if you take an electron away, it doesn't matter what it is. If you're comparing, iron to iron 2 plus, that iron 2 plus has to be smaller. Just because we're taking electrons away. Now, when we have a metal, we're never going to find that we can, in a stable way, add electrons into an atom. So for metals, they only ever lose electrons to form stable compounds. So we're never going to have like iron 2 minus or iron minus. It's going to be the non-metallic elements that add electrons to themselves. If we go O minus, that O2 minus is bigger than oxygen because we've added 2 extra electrons. And so this is larger as a result of having more electrons. So anions are always larger than their neutral counterparts because adding electrons increases their repulsions with each other, so we grow in size. And so then let's do some comparisons of size. So like if we're comparing sodium so let's break down the isoelectronic series first. So let's compare a set of ions. So O2 minus, F minus, share being anions that have 10 electrons. So oxygen has an atomic number of 8, fluorine of 9. So oxygen had to gain 2 electrons to get to the noble gas count of 10 electrons. So 10 electrons is how many electrons that neon has. And so this electron count here is that neon configuration count. And so then when you look at fluorine, also has 9 electrons, add 1 through a minus charge to go to F minus. So F minus also has 10 electrons. And so then we go to sodium plus, magnesium 2 plus, aluminum 3 plus. If you take 1 electron away from sodium, then it becomes an ion that has 10 electrons as well. Magnesium's atomic number is 12, take 2 electrons away, it goes to 10 electrons as well. So all these ions here share the trend of having 10 electrons. And so all of them have 10 electrons. That's what we mean by isoelectronic. So iso, of course, is the prefix that means same. So the same electronic configuration are these ions that share having 10 electrons, 10 electrons in total. And so then if you're thinking of having a configuration that has a nucleus that then has a 1s2, 2s2, 2p set of orbitals, so that's our 10 electrons. So which atom do you think, or which ion do you think is going to be smaller? The one that has an 8 plus or the one that has a 13 plus? So think about this charge here. It varies on this trend from 8 plus all the way to 13 plus. 13 plus is going to pull that same kind of electrons in to be a lot smaller than if we had only an 8 plus. So when you're comparing the size, notice that O2 minus is a little bit bigger than F minus because it only has 8 plus protons to pull in 10 electrons. Fluorine picks up an extra proton, so it has 9 protons to pull those in. Sodium has 11 protons to pull those in. Magnesium has 12, aluminum has 13. And again, I'm drawing my sign backwards. Second time I've done that. So we want to go this way because our size is decreasing. So we get a decreasing size. This is our smallest over here for aluminum 3+. This is our largest over here for the O2-. If we had N3-, it'd be even bigger. And so for an isoelectronic series, the way we compare their size is to compare the number of protons. And so when we start comparing size, there's a couple of different ways we can think of how two atoms compare in size. If they're uncharged, we use the periodic trend. We use a periodic trend that size decreases left to right and increases from top to bottom. If we're comparing sodium plus to chlorine minus, we have to think of their relative isoelectronic series. And so let's compare a few things here. So let's compare the size of sodium to fluorine if they're both neutral. So we're comparing sodium and fluorine as neutral atoms. So this means that they each have, 11 protons, 11 electrons for sodium, 9 protons for fluorine. We use the periodic trend. So this is using the periodic trend of size that decreases left to right. And so one of the ways we can compare sodium is to perhaps lithium, that we know sodium is bigger than lithium from top to bottom trend. As you go from top to bottom, size is increasing from top to bottom. And then we also know that fluorine is smaller than lithium, just in terms of a neutral atom. So neutral lithium smaller than, neutral fluorine smaller than neutral lithium because size decreases left to right, but then size increases from top to bottom. So if we know sodium is bigger than lithium, and we know lithium is bigger than fluorine, then we know for sure that sodium is bigger than fluorine. So which one of those is bigger? Sodium's bigger, fluorine is smaller. And so that's how you can compare from neutral atoms. We use the periodic trend. Now, when we compare sodium to sodium plus, this is just using the idea that cations are smaller. So we know sodium plus is going to be smaller than sodium because we've lost an electron. And cations always go smaller than their neutral counterparts. But we know that anions always grow larger than their neutral counterparts because we add an extra electron, increase those electron repulsions. So fluoride is bigger than fluorine. And so now if I'm comparing the charges and then the sizes of sodium plus and F minus, this is then when you use your isoelectronic series and say they both have 10 electrons. So this is an isoelectronic series. Which of those atoms is capable of pulling that same electron count of 10 electrons in more closely? We got to compare the number of protons in the nucleus. So sodium plus becomes smaller than F minus, and you flip the trend of size. So uncharged, sodium's bigger. Sodium's a lot bigger. So sodium's a lot bigger than fluorine uncharged. But as soon as you take an electron off of sodium, maybe you give it to fluorine, fluorine becomes bigger, sodium becomes smaller, such that now sodium is smaller as a cation than fluorine is as an anion. And so this, we have to use the isoelectronic series. So so this is trying to tell us, how do we compare size? Uncharged atoms, we just look at our left to right trend. We look at our general periodic trend for changes in size relative to the periodic table. And then whenever we're comparing ions, we have to think either compared to its neutral counterpart, what's the relative size, or compared to another ion of equal electrons, we then compare using the isoelectronic series. Just to make one other comparison, if I'm comparing sodium plus to K plus, where we're comparing 10 to 18 electrons, this just becomes a top to bottom trend. That, of course, potassium is going to be bigger. If I'm comparing the size of F minus to chloride, then of course chloride is going to be bigger because it's further down from top to bottom. So when I'm comparing like charges to each other, I can then just make use of the general periodic trend. So if I'm comparing F minus to Cl minus, I just use then the general periodic trend of changes in size. Of course, having 18 electrons, as chloride has, is going to be bigger than having 10 electrons that fluorine has. And so we can just think for our isoelectronic series of 10 to 18 to 36, centered around chromium, that we're going to increase in size as we go down each successive isoelectronic series. Okay, so let's just talk about a little bit about ionization energy and then wrap up for today. So ionization energy is the energy that's required to remove an electron. To be fair, and this somewhat comes up a little bit later, is that these are for gaseous atoms, just so that we're kind of trying to compare apples to apples, because if you notice, as you go from left to right, we go from solid to sometimes liquid to gas. We don't want to look at the different properties that a certain solid has that the gaseous element doesn't have. So if you look at ionization energies for solids versus gases, you'll see a lot of non-apple to apple type comparisons that can be made. So in order to compare elements with each other where the only thing that you're really comparing is the difference of the ionization energy, that there's nothing else in terms of like a solid lattice energy going on, we compare the energies of the gaseous atoms, the energy it takes for them to lose an electron. And the first thing that I think that we should mention is that all the elements on the periodic table require energy for them to lose an electron. So if you want to pull an electron off an atom, there's some negative, positive, attractive force that has to be broken. And you can kind of come back to Coulomb's law that there's the energy of electrostatic attraction is kappa Q1, Q2 divided by D. So you have the two charges, maybe the charge of the electron, the Z effective, that there's some charge that you're breaking forth so that all of our ionization energies have to be greater than 0. So all these are positive values, just to make sure we see that. But then the I1 is the energy it takes to remove just the first electron from the element. So to remove one electron off of sodium, it's 496 kJ per mole. So if we have a mole of sodium, it would take 496 kilojoules of energy. Then we would convert all those sodium atoms as a gas to sodium plus cations still in the gas phase. So the delta H of that process would be defining the ionization energy, which would be plus 496 kJs per mole times 1 mole, so 496 kilojoules to ionize a mole of sodium gaseous atoms to sodium plus gaseous anions. And so then if we wanted to take those sodium plus atoms and try to take a second electron off, if I wanted to then say, well, how much energy does it take to go from sodium plus to sodium 2 plus? That's going to take a tremendous amount of energy. Remember, we went from a 1s2, 2s2, 2p6, 3s2, low effective charge, pretty low ionization energy. If I want to try to take away the second electron from sodium and go to sodium 2 plus, I have to take a core electron away. Notice that that's about 10 times as much energy. So it takes over 4,000 kJs per mole. So effectively, we're never going to sodium 2 plus. So sodium 2 plus is not going to be something that we commonly encounter or ever encounter in a stable compound. And so ionization 2 is the energy it takes to remove the second electron, and each successive electron takes more energy than the previous. And so the I2 is just the energy to remove just the second electron. So if you want to get the sodium plus, you got to take, or if you want to get the sodium 2 plus, you got to take the first electron away, then you got to take the second electron away. So it's these two values here added together. So for magnesium, if we want to remove 2 electrons, we got to take 738 kJs for the first electron to be removed, 1451 kJs for the second. So it takes about 2,000 kJs per mole of magnesium to go from magnesium to magnesium 2 plus. If we want to go to magnesium 3 plus for some reason, it takes a tremendous increase in energy. So the successive ionization energy always greater than the previous, but then once we remove a core electron, it's like 5 to 10 kJs per mole higher than that previous electron was. So a big jump in energy for removing a core electron. So in other words, we're not removing core electrons in any kind of stable manner. So now notice that as you go across the periodic table, which is going down this particular group. So if you go, as you go from sodium, magnesium, aluminum on a cross, so this is going left to right. So just notice that this is our left to right trend. This is shown top to bottom in this table, that we see a general increase in the ionization energy. You can most see it pronounced if you just look at argon. If you look at these elements here, they're higher in ionization energy than the left side elements. We do see a zigzag in the trend. I don't want to be too, let me actually show you this slide here. You can kind of see, you go sodium to magnesium, you get a drop and you get an increase, get a little bit of a drop, get a little bit of an increase. This is kind of a nuance I don't want to get too bogged down by, because the ionization energy is the outermost electrons ionization energy. So we're ionizing s electrons here, we're ionizing p electrons here, we're ionizing a spin paired electron here. So you see variability from left to right just due to some, just some like configuration anomalies, I would call them. So the configurations aren't the same. The type of orbital you're removing an electron from left to right is variable, because you're removing from s versus p electrons, which have a different nature, and then spin paired orbitals have different natures than spin unpaired orbitals. So there's a configuration anomaly, but the general idea would be, as you go from left to right, as the effective charge is increasing, the size of the atoms is decreasing without a periodic break in that trend, that the attractive force of those electrons is increasing. And then we just see a few weird configuration anomalies that leads to there not being a straight increase from left to right in ionization energy. But the idea of ionization energy, it shows you as you go from left to right, attractive force is increasing between the outer valence electrons and their nuclei due to the increase in the charge and the decrease in the size. So both of those trends, if you think of Q1, Q2, divide by D, if you can increase the magnitudes of these charge and you can make the ions closer together, then if you think of the energy of the electrostatic attraction, that the magnitude of that attractive force is increasing if you go to higher magnitudes of charge, if you put them closer together. So taking two charged particles that are closer together, they're more attracted as a result of being closer. Take a plus and a minus far away, there's no attraction there, but if you put them closer together, they have a greater attractive force. So we want the charges to be closer and higher to be a more attractive force. The ionization energy is kind of showing us that as the atoms become smaller, the effective charge goes up, that we get a higher ionization energy as a result. So left to right, a increase, but with a periodic inconsistency that I wouldn't be too worried about. It's a configuration issue why we get that periodic inconsistency. But the idea is that the attractive force does increase from left to right, and then top to bottom, we get a decrease. Why might we get a decrease from top to bottom? Atoms are bigger. The valence electrons are further away from the nucleus. And so being further away weakens that attractive force. And so it's because as you go from top to bottom, the distance of that outer valence electron is increasing, that lowers the attractive force. Now you might have said, well, didn't the Z effective increase a little bit from top to bottom? But it doesn't tend to win out. A few times it does. And so this is where I was mentioning there might be a few instances where there's a few elements you can see that break the periodic trend of generally decreasing ionization energy from top to bottom, and that's because of Z effective issues. Again, nothing to really worry about the nuances of that being part of a test question, but just the nuances of there being issues of size and charge and how we can think about what those are and how atoms are kind of putting it all together for us. All right, so we will summarize a few of these things on Monday, just to kind of, or on Wednesday after our test, to rehash some of the things we just talked about, because I know this is quick, but chapter 7 is a quick chapter. Chapters 8 and 9 are where we're going to have most of our test questions from, so we want to focus chapters 8 and 9 as much as we can after midterm 3, so we can be as prepared as we can be for midterm 4 down the road. All right, guys, good luck tomorrow, and I will see you back here Wednesday.